Here's an example acceleration problem, calculating the acceleration. The equation for acceleration, the average acceleration, is delta v over t, change in velocity over time. We're going to assume the acceleration here is uniform. It doesn't have to be, but all the problems we'll be having in the near future will be uniform, smooth acceleration. Another way to look at this equation is A equals v sub f minus v sub I over t. As I mentioned before, v sub f is the final velocity of the object. V sub I is the initial velocity of the object. So in this case, the acceleration is v sub f, which is 67 meters per second, minus 25, divided by the 8.3 seconds. We'll put the units back here in a second when I do the computation. So 67 minus 25 is 42. Then you divide by 8.3, you get 5.1. And that's meters per second squared. That's the rate at which the velocity is increasing. You should also include the unit or the direction, in which case would be west, because that's the direction in which the car is speeding up. So that would be our answer for this one. Here's a second sample problem. This particular truck is speeding up from 42 miles per hour to 75 miles per hour in 4.9 seconds. The issue here will be the units. What do we do with the units? Because the acceleration is 75 miles per hour. You got to make sure these two are in the same. They are miles per hour. That's the key so far. Minus 42 miles per hour over 4.9 seconds. So if you do the math here, 75 minus 42 is 33 divided by the 4.9, and that's 6.7, but it's not meters per second squared. This maybe gives you a little bit more insight into what acceleration is. This is the average acceleration here, miles per hour per second. In other words, this truck is gaining 6.7 miles per hour each second's worth of time. So it's the rate at which the velocity is changing, and it's speeding up in the south direction. So we need to include that in our answer. 6.7 miles per hour per second. You could have all kinds of weird units like 6.7 miles per hour per year, or 6.7 meters per second per century. What always happens is you have a distance, like miles, and then two values of time. The standard will be if we do meters per second, we call that meters per second squared like we did in the previous problem. All right, one more example. Here's the third example. Once again, you check your units first. You're slowing down from 26 meters per second to 11 meters per second. Those need to be in the same units, if not, convert them. The issue in this problem is we're slowing down, so what do we do with that? Well, the acceleration is v sub f. In this case, v sub f, the final velocity is 11 minus 26. Those are both meters per second, so we're good there. And the time is in 3.6 seconds. So the acceleration is going to be 15 divided by 3.6. So that comes out to be negative 4.2 meters per second squared. That usually indicates something that's slowing down. Slowing down here in the north direction. The interesting thing about that, and that's the answer, negative 4.2 meters per second squared north. But that would also be equivalent to, and you won't need to know this right now, but for the more advanced topics at a later date, we could also call that positive 4.2 meters per second squared south. It's kind of like a double negative in the English language. If you're not going to grandma's house, you are going to grandma's house. So here, if you're going you have a negative acceleration northward, it's a positive acceleration in the opposite direction, south. It's equivalent to basically gaining speed in the south direction. Even though you're not gaining speed, you're losing speed in the north direction. You're losing speed at the rate of 4.2 meters per second each second.